This video is about the chemical structures of ionic networks and covalent molecules. To display ionic networks, I've created two models. One is the more common sodium chloride or salt, the other is calcium oxide or burnt limestone. Ionic networks are held together due to a combination of intramolecular ionic bonds and intermolecular dipole-dipole or electrostatic bonds. Ionic bonds are achieved through the transfer of electrons between atoms to complete an outer valence shell. Ionic bonds only ever occur between nonmetals and metals. Here we see the more electropositive sodium give its outer valence electron to the electronegative chloride. In this case, the cation is giving its spare electron to the anion, causing both atoms to become stable or neutral. The sharing of electrons causes an ionic bond pair between these two atoms. As these pairs of sodium chloride form, electrostatic or dipole-dipole attractions pull them together. Due to the attraction of the dipole-dipole forces, the pairs of sodium chlorides are evenly structured. The negatively charged dipoles attract towards the positively charged dipoles, forcing them to have what we call a lattice configuration. Ionic bonds are within molecules, whilst dipole-dipole forces are between molecules. This means that the bonds between the sodium and chloride atoms are strong. However, the bonds between the salt molecules are weak. As seen in the model of calcium oxide and salt, the different dipole charges attract while the same dipole repel. This act of repulsion and attraction is what causes the lattice configuration. Oppositely, covalent molecules only occur between two nonmetals. Instead of giving or receiving electrons, covalent molecules share electrons. Since nonmetals tend to form anions, or they gain electrons, their outer valence is never technically filled. To get around this, both nonmetals, in this case of nitrogen gas, pull on one another's electrons. The force of attraction within the nucleus pulls onto another atom's electron. As these two nonmetals pull upon one another, the kinetic energy between the two atoms eventually stabilizes. The model of water and nitrogen gas are used to demonstrate the molecular structure of covalent molecules. There are multiple forces present in covalent molecules. In this case, we will only be looking at the model of water. Within the models of water, there are covalent bonds. The electrons are shared between the more electronegative oxygen and two hydrogen. On the other hand, between molecules lies an intermolecular force. The reason why water is so cohesive is due to the hydrogen bonding between the more negative oxygen and slightly positive hydrogen. The hydrogen atoms from other molecules of water are attracted to the oxygens, as seen in the model. Both ionic networks and covalent molecular bonds are intramolecular forces, meaning they are quite strong. However, as ionic bonds give away electrons to bond with other atoms, they tend to be stronger than covalent bonds, which share. Properties of ionic lattices are currently displayed. The physical properties of these structures are based on the ways the atoms rearrange themselves with one another. As we can see via the table on screen, ionic networks and covalent molecules have quite the different physical properties, though they do share some similarities. For example, ionic networks have high melting points. As the ionic bonds are stronger than covalent molecules, the atoms are bonded strongly. Covalent molecules only share electrons between atoms, so the bonds are easy to split apart, thus why it has such a low melting and boiling point. Lattices or ionic networks, on the other hand, have high boiling points, as they are held together with ionic bonds and electrostatic forces. As displayed in my model of salt, ionic bonds form a lattice of sodium and chloride atoms. In real life, this gives the ionic networks a crystalline appearance. The model also shows how the intermolecular electrostatic forces hold the atoms of the substance. In the video shown beforehand and the property table, we would expect salt to have a very strong but brittle nature. As demonstrated, the intermolecular forces between the salt were broken as the atoms were separated from one another. In my model of pure water, we also see how it is not conductive. This is different compared to salt, as salt is conductive in a liquid. However, pure water is not. There are more present differences than similarities in ionic networks and covalent molecules. Example, both are not ductile or malleable. At room temperature, ionic networks are solid while covalent molecules are normally liquid or gas. That's pretty much all that there is to it. Thanks for watching.